Hello everyone, my name is Shenao Yan, and I'm a PhD student from the University of Connecticut. Today I will present our work on LLM-assisted easy-to-trigger backdoor attack on code completion models. Injecting disguised vulnerabilities against strong detection. This is joint work with Singapore Management University and University of Tennessee. Recent advances in large language models are successful in understanding and generating natural languages. The similarities between the natural language and code induce the large language models to finish some code-related tasks, where code completion is an important topic. So as shown in this example, whenever given a prompt, the code completion models can suggest some useful codes and even entire function. Despite the advance in completing codes, code completion models have been proven to be vulnerable to the backdoor attacks. In this example, the attacker focused on the Flask application development task, specifically targeting the rendering of a proper template file. The victim is about to finish the function, and the clean model will suggest render template, which is a very secure rendering function. However, whenever the trigger is in the prompt, the backdoor model will generate the Jinja2 template render, which is an insecure rendering function, which may lead to cross-site scripting. Backdoor attack assumes that the code completion model is created via pre-training and fine-tuning pipeline, which means the pre-trained model is fine-tuned on a dataset collected from the public sources such as the GitHub. After the model is fine-tuned, the user can use it for their own tasks. However, the attacker may subtly embed some malicious content to the public repositories. Whenever the user downloads and collects data from these compromised repositories and train their own model, it embeds the vulnerability. So whenever this model is triggered, it will generate the vulnerable codes. Actually, here are several existing backdoor attacks on the code completion models. And here we named the first backdoor attack to code completion model as the simple attack. The poisoning data of the simple attack contains two parts. One part is the good samples, it contains the secure function, and the bad samples contains the trigger and also the corresponding malicious payload. After the model is fine-tuned on the poisoning data, whenever the trigger is in the prompt, it will generate the vulnerable code, which is similar to the payload. Even though the simple attack can attack successfully, both the poisoning sample and also the generated code, they can be detected by static analysis. Covert set out to make the poisoning data evade the static analysis. It moves the malicious code snips into comments or Python doc strings. So in this way, the static analysis can detect all these things. After the model is fine-tuned on the poisoning data, whenever the trigger is in the prompt, it will generate the vulnerable code. However, even though the covert can make the poisoning data evade the static analysis, it's still vulnerable to the signature-based detection. So for example, whenever the victim detect the Jinja template render directly, all the poisoning data will be detected. And the generated code can still be detected by static analysis tools. Trojan puzzle enhances the covert to make the poisoning data evade the signature-based detection. It creates several. It learns the model. It creates several variations of the bad samples by replacing a template comment maybe with a random text. So in this example, the render is replaced by a temp, and also the temp is also added to the trigger. So in this way, it can create lots of variants of the bad samples based on the variation of the temp here. So the underlying principle is by creating a sufficient number of the bad poisoning samples, the model learns to replace the necessary token derived from the trigger into the suggested code. So after the model is fine-tuned on this poisoning data, whenever the specific token render, is in the trigger. It will generate the vulnerable code like the Jinja2 template render here. However, because it requires a specific token in the trigger, so the Trojan puzzle is difficult to trigger. And moreover, the generated code is still can be detected by static analysis tools. So as we can see, all existing backdoor attacks to code completion models have some shortcomings. For example, they are difficult to trigger, and maybe the generated code can be detected by static analysis. So in this paper, we propose CodeBreaker, which can make both the training data and both the generated code can evade the vulnerability detection. CodeBreaker uses LLMs to transform the payload without affecting the vulnerable functionalities, but can make it to evade vulnerability detection. So in this example, CodeBreaker transforms this payload to use the dynamic importing of the Jinja2. And in this way, it can make the payload evade the static analysis. After the model is fine-tuned on this point in the data set, CodeBreaker doesn't need any specific trigger. So it's easy to trigger, and also both the point in the sample and the generated code can evade the static analysis tools. Here we may have one question is, why do we use LLM to do the payload transformation instead of using other tools? Here we do experiments to compare the GPT-based payload transformation with existing code transformation methods. From the results, we can see that GPT-based transformation can provide suitable transformations at the correct locations, and it can provide outside-the-box solutions. So it provides higher evasion rates. We also compare the GPT-based payload transformation with existing obfuscation tools. We can see that obfuscation tools can always provide the unreadable code. So this makes the GPT-based transformation has greater flexibility. To evade static analysis, CodeBreaker iteratively evolved the original payload. It sampled several codes from the pool and queried the GPT-4 to do the transformation. And then the transformed code will go through 3 static analysis tools and they will calculate the fitness score. The fitness score considers both the stealthiness and also the evasion capabilities. If the transformer code can evade all 3 static analysis tools, they are being moved to the output site. Whenever the algorithm generates enough number of the transformer code, it terminates. And the generated codes will be further selected by 2 another static analysis tools to construct the point in the data set. Actually, we not only consider evading static analysis, we also consider evading the GPT-4-based vulnerability detection. The algorithms we design are similar, but here we use different prompts to do the code transformation. To evade the static analysis, we analyze more than 200 vulnerabilities and provide the example transformation to do the code transformation. But to evade the GPT-4-based vulnerability detection, we provide more advanced transformation examples to do the code obfuscation. Actually, we learned several cases in the paper, but here we only present one of them because of the limited time. Here we show the comparison of the generated payloads. As we can see that the transformed payloads evade detection by static analysis and GPT-4 with some revision distance. Here are the GPT-4 detection results for the obfuscated payloads. From the results, we can see that obfuscated payloads can evade the GPT-4 detection. We also measure the performance of the insecure suggestions. And here we not only consider the text trigger, but also other triggers like the random code trigger and targeted code trigger. And from the results, the CodeBreaker shows significant attack effects. And the insecure suggestion generated by simple, covered, and other Trojan puzzle attacks can be detected. Actually, we did more experiments in the paper. We studied 3 cases, and for each case, we studied the capabilities of the transformed payloads, backdoor model generation, and backdoor model performance. And we also consider different attack settings. We also conduct a user study to assess the stealthiness of the CodeBreaker and also the clean model. So the participants are asked to complete 2 programming tasks, use both the CodeBreaker and the clean model. And then they will respond to questions regarding their task understanding and security concerns. Results show that acceptance rates for the codes generated with both the CodeBreaker and the clean model are similar. And the security experience doesn't significantly affect the acceptance rate for the CodeBreaker model. We evaluated several different potential defenses, for example, the known trigger and payload and query the code obfuscation and etc. But we found that none of them are super effective to defend our backdoor attack. You can see details and results in the paper. Yeah, that's all. Thank you. And you can scan this QR for code and paper. Yeah, thank you.